All right, here's a cool problem. We've got a ladder of length L and mass 2m with a firefighter of mass m 3/4 of the way up the ladder. The ladder is about to slip. Find the force of the wall on the ladder and the force of static friction of the ground on the ladder. And we're going to say that it's a frictionless wall. In other words, we don't have to worry about the force of friction. This wall is frictionless. So the ladder is about to slip. You might want to ask yourself, which way would this ladder need to move to make it less likely to slip? That's a really good question. It's not directly related to this problem, but let's use this as an opportunity to do some problem solving, just some conceptual problem solving. If the ladder moves, the bottom of the ladder moves closer to the wall, will that be more or less likely to slip? Well, let's take it to an extreme. Here's our wall right here. If the ladder was like this, notice that the ladder would just be not slipping at all. Might be hard to balance, but it wouldn't slip at all. So you can see that if we want the ladder not to slip, we move it closer to the wall. But that's separate from this problem. Let's go ahead and just take a look at this problem and see what we can do with it. So problem solving strategies. We got to draw a free body diagram. What object are all these forces acting on? It's the ladder. So let's draw a free body diagram with all the forces acting on the ladder. So we've got the mass of this person. Let's go ahead and draw that force acting right at that point. And that force is, in fact, mg, because the person and the ladder are not accelerating, so we can use mg for the force of the person on the ladder. How about the force of gravity on the ladder? And where does that act? Well, halfway up, this is the center of mass of that ladder. So this distance right there is L over 2 up the ladder. That is the force 2m. That's the mass of the ladder times g. I'm going to make that a little bit longer, so just we are conceptually understanding that's a greater force than the weight of the person. Okay, any other forces acting? Well, as mentioned, we're trying to find the force of static friction. That is acting right here at this point. So I'm going to draw that right there. Fs. It's acting at the point of contact of the ladder and the ground. Are we done now? Well, we're actually not. There is a normal force at this point right here where it's touching the ground. I'm going to call that N1. Now you can use F sub N, but I like to use N because if I have subscripts, then I don't need to double subscript it. So that's the normal force due to the ground. You might guess I've planned ahead, and there's going to be another normal force. Where is that? If you guess the wall's force as another normal force, you are correct. So I'm going to call this force the force that the wall is exerting on the ladder, N2. Now, you can see it's a frictionless wall, so there's no up or down forces of friction. Are there any other forces acting on this ladder? Nope, we've got them all. So we've got our free body diagram. Let's pick an axis of rotation. Now, there's many, many possibilities. In fact, really, there's an infinite number of possibilities. But a lot of times what you want to do is simplify your situation for torques. Can you find a point on here where a lot of forces are acting that I don't want to deal with yet, so I can make my axis of rotation there, figure some stuff out, and then go back and figure out the rest of what I need? I can see a couple of points where that might be useful. And what I'm going to do is I'm going to choose this point as my axis of rotation, where the normal force 1 is acting and where that force of static friction is acting. I'm going to choose that. And I may say, but you want the force of static friction. I do, but as you'll see, it's going to be a lot easier to figure out some other forces, which will easily give me my force of static friction. That just comes from experience. But yeah, there are many axes you could choose and still be able to figure this out. I'm just going to choose that as the axis of rotation for now. So let's go ahead and we got that axis of rotation. Let's pick a direction for positive. So I am going to arbitrarily choose clockwise as my direction for positivity. So let's call this direction around clockwise. I'm going to call that positive. So let's say if that were positive, which way is going to be a positive x direction? Well, if we look at this end of my ladder right here, if that were going around clockwise, looks like down would be positive. That end going down would be positive. And that also would be moving to the, will that be moving right or left? That'll be moving to the right if it's rotating around that way. So there's my positive direction horizontally. That is not absolutely essential that you do that. You can define other directions. In statics, you can do that. If you're doing rotation with actual angular acceleration, you have to have your angular acceleration angle agree with your linear acceleration direction in terms of like positive or negative. So let's go ahead and we got our directions of positive for rotation and translation. Let's just jump to our torque equation. The net torque about our chosen axis, we chose that star point there, is going to be equal to 0. Which forces are exerting torques? I'm just going to again write them all. We got the torque due to the N1. We got the torque due to N2. We got the torque due to the force of static friction. Torque due to Fs. We got the torque due to the person. We got the torque due to the weight of the ladder itself. And those are all the forces we have. Those are going to all add up to 0. Cool. Now, we can simplify this slightly because the torque due to N1 about this axis, that's 0. The R is 0. The displacement from the axis of rotation to where the force is applied is 0. Same for Fs. That's going to be 0 too. Notice that this is acting at that point as well. So displacement from axis of rotation to point of force application is 0. Those are gone. N2 is exerting a torque. Person's exerting torque, and the weight itself is exerting torque. Let's figure out which directions those are in. Due to N2, if I call clockwise around this axis positive, that's going to, if this were the only force acting, N2, that would actually make it rotate counterclockwise. So that's going to be a negative torque. So this will be a negative torque. And I'm just going to write RF sine theta here. That'll be negative, and that'll be RF sine theta. Let's go ahead and indicate what those are. R is the length of the ladder. So that'll be just negative. L is the length of the ladder. Our force acting there is just N2. What is the sine of the angle between them? Well, this angle theta right there is going to be this theta here as well. Now, those are the, if this is our L, notice that those are the tip to tail angles. Again, the actual angle, I'd have to put them tail to tail. It'll be 180 minus theta. I'm going to go ahead and just use theta again. It'll be sine of theta. Even though it's the angle really is a 180 minus theta, you will get the same thing if you use sine of theta. Be careful on that, but it's generally true. You can use the tip to tail angle for torques because sine is very forgiving. Okay, how about this one right here? What is the torque due to the person? Well, I'm going to use RF sine theta again. Now, what is R? Well, the person is 3/4 of L, 3/4 of the length up the ladder. So that's going to be 3/4 L. I'll do plus. It's R is 3/4 of L. The F is where the person is. That's just mg. What is that sine of that angle between them? Now, this is where we got to be really careful. You might just say, oh, that's just theta. It's not. This angle, here, let's figure it out. If this was, that is theta right there, as it turns out, using we have a transversal and two parallel lines right there, so that we know that's theta. This angle is just going to be 90 minus theta. 90 minus theta. And again, you can put them tail to tail to get the real angle, but I'm just going to use the angle tip to tail again because it's right there for me. So this will be times the sine of 90 minus theta. So this theta is a general theta, meaning it's the angle between the r and f vector. And this is the theta that we're using in our problem. Okay, now is that torque negative or positive? Well, that's positive because this force acting alone would exert a clockwise rotation. That is that. Now, how about the torque due to gravity? Also positive because it would cause a clockwise rotation. And that is going to be, again, I'm just going to write RF sine theta in general. The R is L over 2. Notice that where this is acting is halfway up the ladder. That's the center of mass. Gravity always acts at the center of mass. L over 2, the F is 2m times g. That's the force. And then the angle between them is also, we're still going to use that sine of 90 minus theta. And that all adds up to 0. Now, assuming that we're given theta, I want you to look at this equation and tell me how many unknowns there are. We're given the masses, g is g, we're given the lengths. There is only one unknown in this equation, and that is N2. Right there, that's the unknown, one of the unknown forces we're looking for. So we can solve that for N2 and we're all set. But notice that we still have to figure out the force of static friction. So we got the N2, and that's really why we chose this axis, so we could just forget about the force of static friction and forget about the normal force 1 for the moment. We chose that axis so we get N2 easily in one equation. When we got to go back now, though, to figure out the force of static friction, that's where we're going to use our other two equations. So let's go ahead and write those out. Which one should we do first if we want the force of static friction? Well, the force of static friction is in the x direction, so that's going to be the one we're going to have to use first. And I'm just going to write the net force x equals 0. And let's go ahead and find that. The forces in the x direction, I've got Fs, and I've indicated that we're going to use to the right as positive, so that'll be a positive force. Fs. The only other force in the x direction is N2, and that's negative. N2 equals 0. So check it out. Once we have found N2, we've got the force of static friction because it's the only other force horizontally. It's just equal to N2 in magnitude. The only force that we don't know now is N1, the normal force due to the ground, which, well, obviously we're going to have to use the net force in the y direction if we want to find that equals 0. And those forces will be N1 is positive. We've got negative mg of the person, that's negative, and negative 2mg the way the ladder, that all adds up to 0. So if we wanted N1, which actually wasn't asked for, notice that N1 is just going to balance out the weight of the ladder and the weight of the person, and will equal the sum of those. Pretty cool. Now, one more, and I'd say this is my favorite problem because I actually had to use physics to answer an important question in my life. And check out the next video so you can hear about my adventure travel bus. I owned a school bus, and how I needed to use physics and specifically statics to figure out an important safety question. Check out the next video.